All right, good day, everyone. My name is Zekeri Adams, and I'll be talking on the topic leveraging metamodeling language for ontology structuring and validation. Uh, my supervisor is Martin Homola. And I'll just take a brief review of what ontology is all about. So these are different concepts that are related to ontology, taxonomy, thesauri, and control vocabulary. So ontology is simply all about conceptual modeling, structuring classes, relationship with individuals that are related to them. And one thing about ontology that is more or less much more different from other form of classification is that ontology is more richer and it has logical formalization to guide you. And then you can also perform a lot of reasoning tasks on it using reasoning algorithm, and they are logically and grounded in first order logic, in description logics, modal logic, and as the case may be. So some good example of ontology are onto UML and all, which are rich in logic. Just what ontology is all about, a brief definition of it. Philosophically, is the study of being, which is the definition given by Plato. And then in computer science, is the definition given by Gruber in 1993. That is a formal, explicit specification of a shared conceptualization. And ontology, like I said, it has a lot of basic entities in it, like objects, which are the individuals, and then classes are the concepts. The properties could the roles that relate these entities together, like a role that relates a class and a class together, and an individual, and then the attributes with like the data properties, like the age, the distance of a place, and the rest. And then the roles are like the entities that an individual assume in a relationship. For example, I can say Peter is married to Esther, and the role that Peter plays in that relationship could be like the husband, and then the role that Esther plays is the wife. So these are two different things that we are looking about in terms of relationship that exists between entities in ontology. Now, ontologies, like I said, is more of conceptual modeling, and so it has the T box, the arrow box, and then the A box. The T box are more of the intentional knowledge, which define the classes and some relations that exist within these classes. For instance, we can say student is a person. So this is an intentional knowledge. For example, student is a person. That means the class of students are more or less subsumed in the class of persons. And also, another form of relationship is the part of relationship, like department is a part of university. This is also knowledge that you can find in the T box, the terminological box of an ontology. And then the A box are more of the extensional knowledge, which is like the assertion. For example, John is a person, which is an instance, an assertion knowledge that we are talking about. Or Monday is married to Ruth, which is an assertional knowledge also for the A box. And for the arrow box are more of complex relationships that exist in this knowledge base. Such relationship can be the brother of someone. If someone is the brother of someone and that person has a father, then you can say the brother becomes the uncle of him. So this is form of relationship that you can find in the arrow box of the knowledge base. Okay. So some ontological languages include something like the web ontology language, that is all, and then the resource description frameworks. These are grounded in logic, and so with this logical framework grounded in them, we can perform reasoning tasks on them, and then make inferences from this form of formalization. And also another form of representation of it, we can represent them using XML, and we can query these ontologies using the Sparkle query. And some tools that we can use in structuring our ontology. We have a lot of tools like Protege, which is a well-known tool for structuring your ontology. This is just a link for. This is just a brief overview of what ontology is all about, and so this is more like the foundation of my research itself. Now, in the case where you have an ontology being structured by different persons, so if, depending on the context and depending on what the ontology engineer wants, I can have a case where you have a class. Now, being, instead of individuals, in structured ontologies, individuals are usually instances of classes. And so you could have a case where a class becomes an instance of another class. And that, it depends on the perspective of the different individual, and that's what the definition is trying to tell us, that its perspective is simply when you have different modules of ontologies, and depending on the perspective of the ontology engineer, where you have a class, and then that class can be an individual in another different ontology. And so if you have such a case where a class becomes an instance of another class, in that kind of scenario, we have metamodelling in ontology. That is where my work is more focused on, which is metamodelling in ontology. For example, you have this. This is a class for the biological taxonomy. You have the class species, which are instances of taxonomic rank. So usually in ontologies, individuals are instances of classes. But now you have a case where classes are now instances of other classes. Lion is an instance of the class species. And so in this scenario, we want to see how to have a framework to model with this kind of situation, in this kind of domain, where classes are now instances of other classes, no longer individuals. So in this kind of classification, definitely you know that there will be multi-level form of classification. And in that case, you would have a case where you have a model, and when you have a model, it will generate a meta model because a class becomes an instance of another class. And so in that multi-level kind of classification, you will have a meta model, and that can also lead to a meta-meta model and a meta-meta model. So it's more of a different level of a different form of classification level. And in that kind of scenario, what a meta model does for us is to give us a framework for which we can generate a model. So we can easily say that a model is now an instance of a meta model, and then a meta model becomes an instance of a meta-meta model, because the framework for a meta model helps us to create a model, and the framework for a meta-meta model gives us a background for generating a meta model. Okay. So this is just a very simple example. This is an example where you have Jeffrey and Janet are instances of the classes man and woman. So at this instance level, we could say this is just my first level, like a model. And then you have the case where man and woman, these are classes now. Another level, which is, I classify them as level 2, which is like my meta model. And then the other case where you have another class, gender, person gender, which is like the third level. And so you could have domains that exhibit such a thing. So with this explanation I just gave, we're going to focus more on this talk on multi-level modeling theory, which is a theory that gives us a guide on how to model in such complex domain, and also another form of meta-modeling language again, which is Puro, and then its formalization, and then we are going to consider its logical validation and how to a simple application of such language in a knowledge base that exhibits such form of multi-level classification. So the multi-level modeling theory, which is MLT, is a framework that is built with deep instantiation, and it's built on types and individuals. And it also, in this multi-level classification, we can consider kind of relationship that exists between different levels in form of intra-level relationship and then cross-level relationships. And such intra-level relationship could be like a specialization relation, which is in form of the subsumption relationship, like a subset kind of relationship. And then subordination relationship, which is like the part of relationship that we discussed earlier. So if you say a class is specialized on another class, it's more like saying every instance of class A instance of class B, like subsets of it. And then in terms of specialization, it's more like if I have a class T1 and a class T2, so I can say T1 is subordinate to T2 if for all instances of T1, there exists an instance of T2, and those instances are proper specialization of those instances in T2. So this is like, when I say proper specialization, it's more like proper subsets, like just what proper subset is all about. Okay. So an example is the class person adult type is a specialization of the class person gender age type. So this is just what an example of specialization relation is, and that of subordination relation is. It's what I've captured in the diagram. Then what I just explained was more of the relationship that exists within a particular level. What about relationship that exists between, if I have the first level and then a higher level above it? We could talk about relationship, and that's like the power type relation and then the categorization relationships that exist. So, for example, if you look at this diagram here, we see that the class person type is a power type. It exhibits a power type relationship with the class of persons, because the power type relation is just similar to the idea of power set. It means that every specialization of the class of persons are instances of the class of person type. So it's just the idea of power set. That's what power type relation is all about. And categorization relation can take the form of disjoint categorization, partition, and then completeness form of categorization. So these are different relations that kind of exist between a type and a type higher than it. Okay. So that leads me to my main work, which is the Puro language, which is another form of metamodeling language. And Puro is also built on this multi-level kind of classification where you have types instantiating other types. So it's a graphical language, and you can use to build a model on your own, which can stand on its own as for building a model, and it can also be used for structuring ontologies, which you can do with the web ontology language also. And it supports metamodeling, just like I said, where you have this multi-level classification in metamodeling ontologies. So Puro language also gives us a good framework for doing that. And it is built on these distinctions, which the B types, the B relations, the B attributes, B objects, B relationship, and B valuation. Now, these B types are universals. Universals are entities that have instances. You can instantiate them. For example, the B types which have instances are also of different levels. We can have B type 1, B type 2. That is more like the first order type, second order type, third, and then as the level increases. And then B relations are also similar to object properties in your own ontology. And they have instances, and instances of those B relations are B relationship, more like data property assertions object property assertions in all ontology. And then B attributes are also universals. They are more like the data property in all ontology, and their instances are B valuations, which are values. They assign values, like more or less in this case, we are looking at literals, not strings. in this case. B objects are more like concrete individuals. It could be concrete individuals or abstract individuals, as the case may be. So these are more of the universals and the particulars, and these are our Puro terms, which we are going to look at the logical formalizations of these axioms using Puro. Okay. So, like I said, Puro also has its own tool for, just like OL, which has Protege for structuring its ontology. Puro also has its own tool for structuring its ontology, which is more like the Puro modeler. And this is the graphical interface of what the Puro modeler is. The B types, the B objects, the B relation, these are what I just explained earlier. Okay. So let's look at the logical formalization of this Puro entities. So in formalization of Puro language, it's more a bit on these 4 different entities. Entities terms. Entities are more like the objects, the relationships, and different things that exist within different domains. And then the Puro terms are the B types, the B object, the B relation, the B valuation, those 6 items I just listed earlier. Values are more of real values, not in terms of string, just concrete values. And then the roles are the relationship that entities play in a particular relationship, the role they play. Like I explained earlier, Peter is married to Esther. So Peter plays the role of the husband, Esther plays the role of the wife. So that is more like the role in this case, not the relationship itself, but it is the role that the entity play in a particular relationship. That is what these roles stand for. And these 4 terms are disjoint terms in our formalization of the Puro language. Now, in the formalization, we said the Puro terms are more of B objects, B relationships, and B valuation. Now, these are particulars because they when we say particular, they have no instances. You can't instantiate them, and they are disjoint terms also. So this is more like the logical formalization of how we formalize these particulars in Puro terms. And then the universals are the B types, the B relations, and the B attribute. They are also Puro terms, and we are saying that if X is associated with a universal, then it means that item can be either a B type or a B relation or a B attribute. And these are also disjoint terms. And if you have a case, if we have that there exists an X, and X is an instance of Y, it means that Y must be associated with a universal. So it means that Y can either be a B type, a B relation, or a B attribute. And particulars have no instances. It is captured with the last axiom there, that if X is a particular associated with a particular, that means it's either a B object, a B relation, or a B valuation. It means that there is no Y, such that Y is an instance of X. So particulars are strictly not instantiated in this case, which is captured in the last axiom. Okay. So also we try to automatize the B types. Like I said, the B types are, since we have different level of classification, so we can have B type 1, B type 2, down to B type N, as the case may be. So these B types N are also B types, which is captured in the first axiom, that if X is associated with a B type N, then means X must be a B type. It's also a B type. And they are not heterogeneous. That's when we say heterogeneous, that means it's a class that is instantiated by, if I have a B type 1, then B type 1 must be instantiated by B object. You can't have a class that is instantiated by a B type 1 and a B type 2. So it's more like a homogeneous class, not a heterogeneous class. And these B types they are disjoint. B type 1 and B type 2, since they are not heterogeneous, definitely they have to be disjoint, because a B type 1 and a B type 2 will not have something in common. Yeah. Okay. And if I have X an instance of Y and Y is a B type 1, then the instance of a B type 1 are B objects. Then instance of a B type 2 are B type 1. Then instance of a B type 3 are B type 2. So since it's more of a classification level, so within a particular level, the lower level more like instantiates the level above it. Okay. And this more like captured in all these axioms, which is. And then in the axiomatization of the B relationship, one thing we realize in that of the old ontology is that it's more of a binary form of relation. But here we can extend that to have a ternary form of relation, which we use the has participant as our form of predicate to capture that. So if you have a B relationship like R, and if R is a B relationship, then the entity that participates in this relationship as X, and then the role they play in the relationship is now what is denoted by rho there. So in this form of relationship, we can have a case where this predicate now captures not just a binary form of relationship, but it captures a ternary and then as different higher form of relationship that we can talk about. And then this B relationship can take different form. They can be of B instantiation, B axioms, or B facts. And these are also disjoint as captured in these axioms. And that of the B valuation, we axiomatize them using the predicate has valuation. So if X has valuation V, it means X is an entity and V is a B valuation. And if you have V as a B valuation, it means that there exists an X such that X will have the valuation V, and for any other term that has that valuation, they have to be, it's a unique form of valuation. So you can't have an entity having two different forms of valuation. So it is unique with this axiom, second to the last axiom there. Okay. So we also try to axiomatize this universals, B relation and B attributes. So like I said earlier, instances of B relations are B relationships, and instances of B attributes are B valuations. And these are universal, so they also give us another form of type, which we call them B type R for a class, like B relation, a class of B relation, we call them B type R. And for also a class of B attribute, we call them B type A. So these are also different from the B type 1s and the B type 2, B type 3, and the rest. So we also have another form of B type, which is B type A for classes of B relations, and sorry, B type A for classes of B attributes, and B type R for classes of B relations. And they are also disjoint from this classes of B type 1, because this B type R and B type A, they are classes of rows. They are classes of relationships, not just ordinary classes that instantiate individuals. So when we have such logical axioms, it is good to have a validation of them so that it gives us to show that this axiom that we have is good for structuring ontology, for correctness, and for also checking for consistency, so that we don't have inconsistency when trying to build with such axiomatization. And to verify that the ontology covers all necessary concept and relationship within its scope, it is good to also validate whenever you have such logical axiomatization. And we try to verify this using a first order logic theorem prover, Vampire, which is built on this syntax. We use this syntax by transforming every first order logic term to this. So for the bottom class, we use this symbol with the hash false on it, and then for the top level class, we use this symbol with the true on it. So with all this symbol, we're able to transform these axioms that we have discussed earlier, and then try to run them with a first order theorem prover. And in trying to validate that, we try to express this and code those axioms that we have using this syntax, and then run it with a first order logic theorem prover, that's Vampire, to check for the satisfiability of our axiom if truly this axiomatization that we have done, if they are true. And in trying to do that, it also verifies that yes, our axiomatization we are satisfied, and it gives us satisfiability of our result. So it shows that these logical axioms are kind of, they provide us a good framework for expressing our ontology and then structuring our ontology in such complex domain where you have classes instantiating other classes. So this is also an example of a Puro model. We went ahead to check for a Puro model. This is just a brief example using the modeler to create a model on its own. And we also try to use this model. We encode them with our first order logic axioms that we did, and then try to check for the satisfiability of this axiom, this model that we have, if this is true. So we did that, and then it shows that yes, this is satisfiable, that our axiomatization were true also. It did not give us a refutation result. So that shows that the axioms were actually correct. Now, in trying to do that, after we did that, we then tried to check for, try to apply this to an existing knowledge base, Wikidata. So to check for to apply our axioms to an existing knowledge base. And in Wikidata, we discovered that Wikidata is also endowed with this multi-level classification types that we discussed, which is metamodelling. And in Wikidata, we try to look at some relationships of items in Wikidata and that of the Puro terms. For example, the item with the Q number entity is also equivalent to Puro's entity, and also classes in Wikidata with these Q numbers are also equivalent to, the description of those classes are also equivalent to what we have in Puro language as B types. And for individuals, they are also equivalent to what we have in Puro as B objects. And so these are just the alignment of Wikidata items with our Puro language. So now what we went forward to do was to check for inconsistencies. Is there inconsistencies in these items in Wikidata, in the structuring of items in Wikidata? So we use the Sparkle query to check that when I have a second order class, because Wikidata also has this multi-level classification. So we ran this query to check that, is it possible for you to have a second order class instantiating another second order class? But from our axiom, for a class to instantiate another class, then it should be a class below it that will instantiate a class higher than it. But in this case, we have a class in the same level instantiating the same another class in that same level. And when we ran it, we found out some results that yes, there are classes in the structure of Wikidata in the same level, a second order class that instantiates another second order class, which shows that there are inconsistency in the representation of items in Wikidata. And also, we also went forward to check for a first order class to check that if there are entities in first order class that also instantiates other items in first order class again in Wikidata. And we also got some results that in the structuring of items in Wikidata, you can also have a case where a class is in first order and also instantiate another class in the same order. So this is just an example of it. An example is this item here with this Q number is classified as a first order class. Now it instantiates another item in Wikidata with this Q number, but this item was also classified as a second order class in Wikidata. It shows that this was, but actually it's supposed to be in a third order class, not a second order class. But from the structuring of item in Wikidata, this item was actually classified as a second order type, which shows inconsistency in the representation of items in Wikidata. And also this is for the first order class, an example for it also. So this shows how important our formalization is in structuring items in knowledge bases. So with what we have here, to verify this inconsistency in Wikidata, we try to encode this also using our logical axiom, and then check with existing theorem provers if this inconsistency were true. And in encoding it, we encode this. This is the logical encoding of it, and then we transform it using the syntax for first order theorem prover, and then we try to run it to check for the consistency, the satisfiability of this axiom. And when we run it and then check, it shows that this is inconsistent, which also align with our result that these are inconsistent representation in Wikidata. Okay. And that is all I have to say.